Let's start. Thank you very much again, another Friday, for coming to the seminars. Today we have Perrine, and I say I remember properly. She's a PhD student from France, and she has been working here with Amanda for a couple of months, doing a short stay that I think it's almost finishing.
Yes, next week.
Well, today she will talk about her research in physics and deep learning applications. So thank you very much, Perrine, and the floor is yours.
Thank you. So hello everybody. Yes, so I'm Perrine. And I come from ENSTA-Bretagne, which is an engineering school in France, in Brest, Brittany. That's where I graduated as an engineer in hydrography and oceanography. And then I decided to start a PhD in collaboration as well with Ronan Fablet from the Atlantic and Florian Sevelec, who is an oceanographer at the Labs, which is a lab in oceanography from space and study mostly physical oceanography. And of course, my director, Angèle Rémaud from ENSTA-Bretagne. And I came here to spend 2 months to work in the team of Amanda. And so here I will present the results of my second year of PhD, but what I've done here will actually initiate what I will do in my first year of PhD. So what's the agenda for today? I will first talk about ocean observation challenges. And then first I would like to explore how to optimize the information that we actually gather from observation on one side, and on the other side to optimize the way we acquire this observation. And we will see that optimizing both sides of it can actually help us to improve our knowledge on fine-scale oceanic processes. So let's talk about ocean observation. By asking why. This is a simple question that I like, because why do we actually observe the ocean? So I'd like to start with this map of the Earth. This is one of the most representative map of the Earth because it is less distorted. And I like it because we can actually see that the ocean is covering a large part of the planet, and it's no wonder that it is called the blue planet. And actually, in fact, the ocean covers up to 70% of the Earth's surface. But we consider that only 10% of it has been explored. And while we are able to map the entire faces of the moon, even its hidden face, it seems like a much more challenging task to achieve the mapping of our own oceans. But okay, do we observe the ocean only for the purpose of exploration? Do we observe them only just by curiosity to know what's in our oceans? No, it's actually to answer some needs of the oceanographic community. One first need is, okay, why do we need observation if we have physical knowledge? Basically, it's because our physical knowledge leads to this famous Navier-Stokes equation that I will not present here today. But they are so complicated that they are actually a million-year problem. So if you find the global solution to these equations, you can actually earn $1 million. So keep it in mind. I don't know if you're inspired for it. But right now, we are only basing our models on some assumptions that have to be checked with observation. And that's one of the purposes of observation. These observations actually help us to discover new stuff about the physics of the ocean and to improve the rest of our models. And finally, it answers one last need, one of them. Well, I mean, there are more than 3 needs, but the one that I identified is that we lack of computational resources to model the whole ocean. So the resolution of our model is limited. But with observation, we can catch much finer resolution of oceanic processes. And okay, but do we observe the ocean only to answer the need of one oceanographic community? Well, why do we actually need to observe the ocean? It's to answer to a much more global challenge, which is currently climate change. So this is one chart from the GA report from 2021, which actually states that 90% of the heat excesses produced on Earth are absorbed by our oceans. How so? Because the water thermal capacity attracts the heat into the ocean. And the ocean has so play a key role in the Earth system and in climate regulation. And by monitoring it, we can actually better monitor climate change. But you know, the ocean has a lot of physical processes in it from different scales. Some are related to interaction with the atmosphere and with the surface of the ocean. Others are completely internal to the ocean, like internal tides, internal lead waves, and so on. We also have the global circulation that is involved, and all of these processes have different interactions. And today in oceanography, one of the big challenges is to quantify the interaction between all of these processes. So we can range all of these processes in one famous chart in oceanography, which actually highlights a correlation between spatial and time scales of processes. So here we would have climate scale, which characterizes processes that last from decades to centuries, and that are like from a few hundreds to a few thousand kilometers. So big processes that have an influence for centuries. Then we have what we call mesoscale, which is to characterize some processes which last from a few months to a few years, a few weeks as well, and range like have a size around a few kilometers to a few hundred kilometers. And finally, we have the submesoscale, which lasts much shorter, like around a day. And finally, microscale. With our ocean model, we can actually resolve all these scales. With satellites, which is one way to observe the ocean, we can resolve these scales. With in-situ data, we can reach a bit of the submesoscale here. But in-situ data are really rare because of the immensity of the ocean. We cannot be everywhere at the same time, and it costs money, basically. So we are kind of limited to mesoscale, and nowadays in the oceanographic community, there is a need to characterize these submesoscale processes to be able to quantify the exchanges between mesoscale and submesoscale processes to close up the cascade of energy, which is taking a big part in climate regulation. Okay, to sum up, we are on a complementary basis. So we have our models that are validated by our data coming from satellites, which ensure a global coverage of the ocean with a regular temporal sampling, which is really relevant since we are trying to quantify some processes which have frequency, a certain frequency. But the inconvenience of satellites is that it only stays to the surface and we cannot reach what's inside the ocean. But you've seen, like, we have a lot of processes happening inside the ocean. So we need in-situ data as well to cover what's inside the ocean. But so to overcome all of these constraints, what latest advances can we actually use for our purpose. One of it is to have to make progress in instruments of observation. Last year, one new satellite was launched. Its name is SWOT, and it brings a new hope to the oceanographic community because it will enable to have a 2D field of altimetric data. What is altimetric data? Is basically the sea level, what we call sea surface height. And this will enable us to reach some new spatial resolution, which are in the range of sub-mesoscale processes. Here, we will, in this seminar, focus on the region that is crossing over the Gulf Stream, which is one of the main currents of the ocean, coming from the equator, going northward, bring this to the Arctic. And at the same time, while we develop new instruments of observation, we have the rise of machine learning, which is linked to computational resources that are increasing. As you can see here, the historic background of oceanography and in parallel, the historic background of machine learning. Everything actually fastened over the last decade because we were able to launch satellites at the end of the 20th century. And from the beginning of this century, biggest progress were made in machine learning. So how can we combine both of these different fields that are sometimes, well, physicists don't like necessarily, machine learning is often seen as a black box. So we need to create some bridge to make each different community understand each other. Because machine learning can actually help oceanography by having faster computation, by computing larger data sets, and by enabling us to make new discovery in oceanography by a better use of observation. So here I will present one deep learning approach that we developed in our team in Brest that enabled us to maximize the use that we will do of our observation. But first, let's have a look at what is done without machine learning. Here I am presenting widespread method, which is called variational data assimilation. And this is a method that is used for weather forecasting, but also in oceanographic models. What it says is that it combines here in green the forecast done by a physical model, and here the representation that we got from observation. But it considers that neither the model, neither the observation are the right representation of the reality. So, because observation has a measurement noise, but model is laid on assumptions. So how do we use these two sources of information to go to an optimal state of the system? With an iterative algorithm. Here, what we try to do is to update our state X, here, which representing the line in red, at each iteration of the algorithm with a small step. This small step is actually representing the variations of f, with f being a cost function. Cost function taking into account the difference between observation and optimal state, and the difference between the model and the optimal state. So basically, at the first iteration, if you initialize, I don't know, your optimal model to something completely random, then the variations of f will be big because we will have a great difference between observation and optimal, and a great difference between model and optimal. So we will update our optimal state a lot, but at some point, these differences will not be that large. And so we reach our optimal because the algorithm will have converged. But this function is not as easy as it is. It has to be manually parameterized to be actually optimal itself. With here represent this parameterization is represented with alpha and beta coefficients. So, what do we do with deep learning? In the last few years, we went beyond neural networks, and by inspiring the architecture of neural networks with physics, because we need to provide more interpretable models to the physical communities. So for the nets, inspired by 4DIVA, presented just before, the neural networks that helps to boost the resolution of the variational problem, basically. Here, it takes into account the observation and compute a model which is replaced by a neural network trained by the data themselves. Then it does, just as before, computes the cost function, it derives it, and then, thanks to a neural network, which is called long short-term memory, which keep in memory the former state of the system. So it is quite practical for dynamics. It actually learned these two coefficients. So this algorithm, what it does, it optimizes a function, variational data assimilation problem by optimizing its cost function itself. And that's what makes it really powerful, because we don't only optimize the states of the reconstruction, but we also optimize the functions that lead us to the best reconstruction. So here we take as input altimetric data, SWOT simulated data, and we will reconstruct the sea surface height. So we will basically interpolate between the swath. And we will as well compute the sea surface current. How so? With which data? We consider the NATL60 configuration of the NEMO model. It's an oceanographic, well-known model. And since it is a supervised learning, it means that we will give to the algorithms a ground truth here. And it will learn from its mistake of representation and iterate until it is close to the ground truth. So we do the training between February 2013 to September 2013 and test it from October 2012 to December 2012. And this is our results. Here, the ground truth as a comparison. Here, what we would have without deep learning, and here, what we have with our method for deep learning. So from the eye, we can directly see that the resolution is much finer on the sea surface currents. And actually, when we compute the error, so here it's actually the error on the SSH, there is a factor of 1.5 in between the reconstruction provided by the classical method of optimal interpolation, which is also like it's a term for the method used here, and here what we got for the varnets. And also what is noticeable here is that the peak in errors here are because it's a moment that where we don't have any SWOT data. Here we have SWOT data, and in between two moments of having SWOT data of the region, there is one moment where there aren't any. And what we see with 4D varnets is that the discrepancy in the error between the moment when we have SWOT data and the moment that we don't have is much smaller than with the classical method. So that's really interesting because it proves that our model is more robust when the observation is scarce. Okay, so now we have seen that we can optimize the use of our observation. Now let's see how we could optimize the acquisition of observation if we want to have a multi-platform approach. So meaning that we want to add some in situ data acquired on the field. Let's imagine in a dream world that we can have thousands of in situ data covering the sea surface currents on our region, plus SWOT data that cannot be seen because the animation is ending, but let's imagine. And put it inside the neural network as inputs, and let's see what would happen. So here are the results. With SWOT-only data, we can see that some of the final scale that's like this one here disappear from the reconstruction when you don't have in situ data. So we lose a bit of finer features. And at the same time, we can see that the intensity of the main currents isn't as good reconstructed as it is with in situ data. So that's what we want. And when we compute the temporal error on our testing period, again, we are dividing our error by 2 when there is no SWOT data. And most importantly, we reach an error below 10%, which is quite good. But what we noticed in this study of Fabli et al. Is that somehow maybe the reconstruction error of the currents could be correlated with, like, there is similarities between this map of reconstruction error and this map of what we call the strain. What is the strain is physical variable which characterize the deformation of the mean field by the currents. So our idea was to target our observation on the places where the strain would be the highest. So we simulated a probabilistic law based on, so a point would be observed depending on the on how high would be the strain. So basically, we are targeting the region of high variability. And now let's see how it can improve our results. Well, we can see that comparing to the one where our in situ data were completely randomly acquired, here the reconstruction is much more smooth and more physically acceptable, right? Again, when we compare the temporal error in our testing period, the error when we target our acquisition with the strain, it's better.
And
But
have the same number of moorings?
yes,
The same number,
it's the
but
same number,
instead
yes.
of random, just in
Exactly.
areas where the stream is.
That's okay. So these are nice results. But okay, with oceanographers could be satisfied with such an error as well. So why bothering ourselves? When we investigated a bit deeply our results, we were able to see that actually targeting the strain could improve the reconstruction of energy transfer. So let's go back to this cascade of energy. Here I thought that it would be climate and mesoscale as mean field currents in our model, and we would associate the smaller scales of our model to anomalies. And what we are studying here is a transfer of kinetic energy between these two. So here, I computed the kinetic energy transfer on our region. So you can see that in yellow, sorry, it's when the current is gaining some energy from the mean field, and in deep blue, it's when it is losing energy to the mean field, so dissipating basically. And what we see with our 3 different models, so one with only SWOT data, one with in situ data randomly acquired, and one when we target the strain, is that Okay, this is still noisy as a reconstruction before. This resolution doesn't seem really good. This seems okay, but it's only about it seems. So maybe we can do more, investigate more quantifying results, right? Here, however, when we plot the differences map, so the difference between this map and the ground truth, this map and the ground truth, and this one with the ground truth, we can see that the differences, like we feel that here the differences are of much smaller scale than these ones. So let's check this out. Here, what we did is that we computed the temporal correlation on our testing period. Correlation evaluates how close our model is to the ground truth. So what we want here is to have a red square. And we can see that the map that we obtain from our model when we target observation from the strain is more red than the others. But more importantly, around the strain, of course, since we have more data here, it is better. Now, when we compute the spatial correlation, so on the whole testing period, we did the average of map like this, on correlation between on how this could resemble to this for each day. And we notice that our model, when we target the strain, has a correlation of more than 90%, while when we don't target it, it's around 75%. So, and it's much more stable even than these other models. But okay, Perrine, this is nice, you might say, but does it actually answer your question? Does it capture smaller energy transfer? So I promise this is the last one. Here, I plotted, so on the x-axis, the wavelength of our oceanic signal. Wavelength is the equivalent of size, but in frequency domain, so it's just the invert of the size. And here on the y-axis is how much of the signal we actually capture. So we can see that with our model, not only we capture like a better signal for all of these scales, but also we can reach a better resolution. Like we can divide the resolution of the model by 2. How do we compute this resolution of processes? We think that we can resolve processes if we get more than 50% of the signal. So this is this boundary in dotted lines. And once our blue lines crosses this one, we say, okay, we cannot reach much further. So here, while we can reach a resolution of 35 kilometers, while here it's 73 and even 77 for a model where we have in situ data that are just randomly acquired. So, okay, some take-home messages now. Observing the ocean is necessary but challenging, and deep learning is a way for us to maximize what we do with our observation. We have seen then that combining physical models, in situ observation, and satellite data could bring us to new results, but only if in situ data can be smartly sampled. That's usually a preliminary work that is done before a campaign, but maybe going towards more innovative sampling strategies would even improve our knowledge of oceanic processes, especially the one of smaller scale. But okay, this was all theoretical, and unfortunately, Santa Claus doesn't exist, I think. So let's talk about what the reality is like, and that's why I came here for 2 months. Is because the team of Ananda and Baptiste conducted a campaign in the Balearic Sea. which was done first to calibrate SWOT, the wonderful satellite that I told you at the beginning, and also to take advantages of these satellites to quantify, to study the smallest processes happening in the direct sea. So they did this campaign between April and May, and I came here just to get to know a bit more their data and to know if I could apply my 4D Barnett model to this data to actually produce a map of sea surface current with the same methods by using real SWOT data, since now the satellite has been launched, and also by comparing with in situ data that have been acquired during this campaign. And food for thought, drifters data are always said as a biased sampling because it only goes to, so this is, a drifter is something like you put in the ocean and it follows the current. So usually it follows the strongest current. But with what I've shown before, it seems like actually targeting the area where there are high variability, meaning a strong current, it could improve the resolution of the processes that we could capture. And with that, I would like to thank you, Ananda and Baptiste, for welcoming me here for 2 months, and thanking the whole team for the warm welcome that you showed me. And thank you all for your attention. And I guess there is some time for questions if I lost you at some point.
Thank you very much. Very nice presentation. Congratulations for your work, really. I just have a question regarding the use of the optimization of the data, in this section.
Yes.
You compare your 4D net
Yes.
results with optimal interpolation.
Yes.
You didn't explain the details about the optimal interpolation that you are doing, but why with optimal interpolation? Because I ask this because optimal interpolation can be very powerful if you optimize also the correlation function and so on. I don't know what kind of optimal interpolation are you doing, because there is a big difference between your result and the optimal interpolation. But
Definitely.
I think that optimal interpolation can do better if you optimize also. I'm sure that your results are better than optimal interpolation, but why do you use it?
That's a great question that I asked myself as well for a year, first year of my PhD. We use optimal interpolation because it's basically doing variational data assimilation on a 2D field. Like the cost function resembles a lot to the cost function that is used for optimal interpolation. And so it is what could be closest to what our deep learning model is doing. But what is powerful with 4D Barnett is that it will learn the coefficients in front of this function. And what I noticed by using this classical method a lot is that it is really tedious to find the appropriate configuration of these coefficients. And if you change one slight parameters in your model, like the number of observations, you have to parameterize again the function, the cost function, and it takes a lot of time. And by having a deep neural network that can learn for us these parameters, it saves a lot of energy and time.
Do you know the parameters and you have used in the optimal interpolation, or
yeah,
you
you can
determine them
at the end? Yeah, I can ask, but I don't know now. Yes.
So I was wondering when you move around, I think you call them moorings, right? So there's sampling points, I guess,
Yes.
to move them from like a random distribution to the optimal distribution. this optimal, the choice of the optimal distribution depends on the underlying currents, right? So this was my understanding of what he said. So in a real field or in a real situation, you would need to know what you're going to measure before choosing where the optimal positions of the points is. So I don't. How do you solve that problem?
It's a circle. Well, usually we use satellite data of the day before, the days before, that can give us a hint of the dynamic of the region before actually deploying the campaign. And that's but yes, otherwise it's an never-ending problem. And but one advances in sampling strategies is what we call adaptive sampling, which is actually acquiring one point of observation, updating the model, and then taking it into account to acquire the next point of observation. And I would like to investigate more of that in my last year of PhD.
So you are using strain for optimizing the observation, but why strain? Why not vorticity or radiated energy? Or have you tested different variables or just the speed of the velocity? If it really improves with the strain.
I only tested the strain for now. Vorticity, we thought about it as well. But I have to compare. We thought about divergence first, but compared to strain, the scale of divergence is much smaller. So it's
very noisy.
Yes.
But vorticity,
but vorticity, that could be also tried without. Yeah.
I'd like to ask, when you were talking about the scale that you call the results in each version of the reconstructed field, I didn't get like these plots, this public shape that you show that changing 70 something kilometers to 30. Like what was exactly that measuring?
This one? Yes. And it's so here it's PSD score. It's signal to noise ratio. So it's the amount of signal that we can have from an oceanic process.
This is spectra?
Yes. Yes.
Spectral density.
That's it. Yes, spectral density. So the closest we are to 1, it means that we recover the whole signal, and when it decreases, it means that we are losing it. And what we said is that if we have less than 0.5 of the signal, then it means that we cannot resolve it properly. So knowing that when the signal is crossing this limit, we say, okay, now we can look at which wavelength we are at, and it will be the resolution of our model. And here we can see that the resolution of it's a bit small, so it's 73 kilometers. Here it's 77 kilometers, and here it's 34 kilometers. So we divide the resolution by 2, and that wasn't expected for us. And also what wasn't expected for me is that the resolution of the model with SO data is better than when we have in situ data. But the quality of our signal is better when we have in situ data than without. Yes.
Yeah, that's one question that I have is that, because your results look better when you have the in-situ data, so how is that your observation scale increases when you incorporate this data, because you should increase it, right? Do you have any idea?
Yes, one thing that maybe it's too much data, because we can obviously see in the reconstructed field that it's noisy. And somehow I think it affects the quality of the signal. And I think that maybe with less, I don't know, with less data, it would be less noisy, that we wouldn't recover as much as signal. That's something I would like to do, is play on the observation budget as well. Also to find the equivalence, maybe we don't need as much as how many data do we need if they are targeted on the strain to reach the same level of reconstruction as the random one. That's the next step.
Sensitivize the number of observations.
Yes.
And put a realistic number, because
Yes,
1,000
really.
But it can be, you mentioned mooring, but it can be a drifter. So
Yes,
it's
for
drifter,
sure. Yes. Or floats, or
It is a velocity, so you need, it's a measurement of
yes,
currents, not temperature.
yes, of
humidity,
currents. Yes, yes. He was first.
I just have one quick question. I think compare this flow with Barnet with the conventional flow of
Yes. Yes, I've done it on another study during my first year of PhD to another model. And actually what we've seen is that when we decrease the number of observation, 4D VAR is not robust at all, while 4D VARNet can still provide really good results and acceptable results on an oceanic process dynamic.
And how expensive is it to run this for the Barnet? Like, is it doable for if you want to do it globally?
Globally, I think that would be much more computation consuming. But for this model, for example, it takes 1.5 hours, I would say, with one GPU. Yeah. And so
You show results in 2D. Did you plan to do that?
pretty.
in 3D?
That was the first plan, but PhD is only 3 years, and I that's an idea in the team, and I think that the junior will work on that.
Okay, so we can leave it here. Thank you very much.
Thank you.